Okay, so I'm going to give a short brief on the examination. This time we have a different way of different format for the examination. So it pretty much covers all the contents that's been taught in the class, um, in all the lectures that I've taught, plus some parts from the the AWR tool. So especially the parts that's covered in the AWR tool. So is the TX line calculator. So during impedance matching and transmission lines, I've talked about TX line calculator. So I recommend there'll be one or two questions from the TX line calculator. So I recommend when you do the online exam, have access to the TX line calculator in the AWR. That will be a straightforward question. If you go through the slides and just play with the TX line calculator, you will get familiar with it. So you can answer that one or two questions that comes in. Basically in the terms of the format of the exam, that will be short answer questions and MCQs and true or false statements. So you're not you don't have to write extensive things in there, but so there'll be probably, so altogether there'll be around 40 questions and you'll get 3 hours. So that 3 hours include the time. So originally the exam was designed for 2 hours, but because this is done online and students may have to upload their workings, this was the university decided to give extra 1 hour. So altogether you have 3 hours. During that 3 hours, you need to answer the 40 questions. Some of them is MCQ, as I said before, so it's very easy. You just need to pick it. You don't need to upload any workings for the MCQs, multiple choice questions. Same for the true and false statements. You don't have to upload any workings. But for short answer questions, for some, the question will say if you need to upload your workings. So in that case, you will have to just get a, do your workings on a piece of paper and then take a photo, upload it there. So just get your logistics around taking a photo, uploading things ready well before the exam, so that you don't put your time towards that. So maybe just or you can just scan your workings and upload it later during the exam time. So that's the brief. So the exam is open book, obviously, because you'll be doing it at home, and even if it was an in-house exam, we will still do an open book. So you can have all your lectures, everything ready so to go through, but I definitely you'll have to go through them before, because you won't have enough time to to have a look at the lecture materials for the first time during the exam. So that's the summary on the exam. I've also decided to do 2 sample questions which will have the exam will have similar short questions from these sample questions or similar sample questions. Now what you need to understand is the sample questions I'm doing are not short answer questions. They are like full question, but in terms of questions in the exam, you will have short answer questions like part A, part B, part C in your exam, online exam. So I will share that screen, and then I'll quickly go through that. Okay, so you should be able to see the screen now. So I will do the workings as I'm okay now. So there are two questions in this sample questions I'm doing. So the first question is from the transistor, the very first lectures that we did. The second question is from the impedance matching, but this is just 2 sample questions, so it doesn't mean that you don't get anything other than this. You'll get things that we've covered during the lectures. Okay, now for the first question talks about a MOSFET as an amplifier, and it's given some parameters, the threshold, KNWOL and VA, and it's given assumption of RG, which is RG here is 1 mega ohm, So first question part is asking is part A, find the RS and RD so that ID equals 0.4 milliamps. So this part A is similar to a short answer question in your exam. So what it's asking is to find this value and this value. Now it's given ID equals ID, the current that goes in the drain is equals to 0.4 milliamps. It is also saying, okay, so we define a few points. So this is the drain, I'll say it's D, and that's the gate, and that's the source. Okay, so if I want to find, so the first thing I want to find is RD. So I know a formula, so I think the right way to write the current ID is, let's say it is ID that's ID. So the ID is given by half mu n Cox WOL VGS minus VTH squared. Now in this case, mu n Cox is Kn. So you know ID is 0.4 milliamps. It's given in the question. Half Kn WOL is 5 milliamps over volt squared. VGS is something that we don't know. That's the VGS here. We're going to find it out first. And then VTH is 0.8. And that's squared. So when you get 0.8 divided by 5, so milliamps cancels out. And that's volt squared, units cancels out. So what you get is 0.4 times 2.8 divided by 5 equals VGS minus VTH, which is 0.8 again. That's okay. Point squared. So that is 0.16 equals VGS minus 0.8 squared. So VGS minus 0.8 equals plus or minus 0.4. Equals either 1.2 volt or 0.4 volt. Now obviously 0.4 volt is not an answer, because if this circuit has to be in saturation, for saturation we need the VGS to be greater than VTH. In this case, that's smaller than 0.8 and that's larger than 0.8. So that's the answer. Okay, so I'll have to delete this, because if I'm going down, so that's the answer. So at the moment is 1.2 volt. Okay, so now what we found, okay, so we found so far VGS is 1.2 volt. Okay, so that means this voltage is 1.2 volt. That's great. Drain and the source. Now for saturation, other condition that you need to satisfy is V drain source has to be at least greater than VGS. And the right condition would be VGS minus VTH, but at least that means VDS has to be greater than VGS. Now at this stage, VD minus VS is VDS. That means VG minus VS, right? Now, So that means this voltage, if this is 1.2 volt, this VDS has to be at least 1.2 volt, the minimum condition. Now, if we go by that rule, we will have this 5 volt, and then you have a RD, and that's VD, and then you have V source, then you have a RS, and that's minus 5 volt, and that gap is 1.2 volt. So altogether that is 10 volt gap. So you can write 10 volt equals the current through this ID RD plus this 1.2 volt plus ID RS. So 10 minus 1.2 is 8.8 volt equals ID times RD plus RS. ID is 0.4 milliamps, so 0.8 divided by 0.4 milliamps, and that's volt. RD plus RS. So that becomes 88, 22 kilo ohms. So this is the only equation we can derive in terms of RD and RS. So that's after that it's sort of a judgment call. So you can pick the RD to be, say, for in this case I'll pick RD to be 10 kilo ohms because it's a design equations design. So you have RS, then 22 minus 10, that's 12 kilo ohms. So you have the RD and RS as 10 kilo ohm, 12 kilo ohm. So it's basically someone can pick RD to be 8 kilo ohms, and then the RS would be 14 kilo ohms. So that's fine. As long as what you pick, you just need to, say that that's what you picked. So that's part A. Okay, find the values of GM and RO. So let me erase this. So far what we know is, now we know that, let me, so I picked this as 10 kilo ohms, and that became 12 kilo ohms now. So GM is given by mu n C ox WOL VGS minus VTH. So we are supposed to calculate GM, which is K in WOL, that is 5 milliamps per volt square. VGS is 1.2 minus 0.8, that's 0.4. So that's 0.4 times 5. And that becomes 2 milliamps per volt. That's your GM. Now RO is the output resistance in the of the transistor, is given by VAOID. So also 1 over lambda ID, which is VA is 40 volt, given already. ID is 0.4 milliamps. So it has a 100 kilo ohm internal resistance, output resistance. So that's part B. Okay. So that's another sub part of the question. Okay, so the next question, part C, is the terminal Z is grounded, so that means that's grounded. Terminal X is connected to a signal source. So this is connected to a signal source having resistance of 1 mega ohm. So the source itself has a 1 mega ohm resistor, and then there's a signal source. And the terminal Y is connected to a load resistance of 10 kilo ohms. So that has a 10 kilo ohm resistance, load resistance, and that is the V out. Find the voltage gain from the single source to load. So basically it's asking, so this is the V signal, you have to find V out over V signal, and that is the gain. So for this one we say it's GV. So it's a bit easier if we do go with the transistor model, small signal model for this. So let me draw this circuit with a small signal model. So now what you need to remember when we do this, all the capacitors and the sources get connected, all the DC voltages get connected to the ground, capacitors get shorted, these things get shorted. So equivalent circuit in this case would look like, maybe I'll write it over here. Okay, so when you, let me erase this part. Okay, so these things get shorted, and that connects to the ground, that connects to the ground. So this connects to a load 10 kilo ohms with the V out, and that is 10 mega ohms with the V signal. So we're trying to find GV, which is V out plus V signal. So if I draw the small signal model for this, I can draw the small signal model in this way. So I have a signal, then I have a 10 mega ohm, then I have RG, which is again 10 mega ohm. Now the model for the transistor would be, so this, if this is plus minus V in, the current that goes through here is GN V in, and the gate is connected, so that's the gate point, and that has a RS to the ground, and it is also shorted to the ground because through the capacitor, this point, this part, and it has the internal resistance, output resistance RO. It also has this RD connected to the ground, which, because this is connected to the ground, that is RD connected to the ground, and this has 10 kilo ohms again connected to the ground, and that's where you get your V out. Now you can simplify this. Now first thing you can easily do is, if you look at this, the V signal is the voltage appearing here. That's a 10 mega ohm, that's a 10 mega ohm. So it's actually equal splitter because there's no current in that gate path, Ig equals 0. So if it's a splitter, the voltage here would be V signal divided by 2. So V in would be V signal divided by 2. Now from this part, if I simplify this, this gets connected to the ground because this is pretty much shorted. So the equivalent circuit would be plus, GM V in, which is V in here, and then you have a resistor which is RO parallel, RD parallel, 10 kilo ohms, and that's your V out. So the current that goes in here is GMV in. That current goes, so that is equal and opposite to the current that goes in here. So we can write GMV in equals minus V out over this RO parallel RD parallel 10 kilo ohms. Now V in in this case GM, V in is V sig, V signal divided by 2, that's minus V out, and that whole thing. So I can get, if I rearrange this, I can get V out over V signal, which is also the gain, equals minus GM RO parallel RD parallel 10 kilo ohms divided by 2. So if you sub in, because you now know GM, which is 2, and then RO is 100 kilo ohms, then this is 10 kilo ohms, then 10 kilo ohms divided by 2. This will come to an answer. So this 10 become 5 kilo ohms and 100 kilo ohms. It will come to something like 4.9. So the final answer, the gain would be minus 4.9. So that means it's inverted, but amplified by 4.9 times. So that's the part C. So that's how you sort of, if you get part by part questions, that's, so maybe you will get a figure and then asked to solve subparts. Okay, now let's go to the next question, question 2. So this is a question similar to that we did in the class. So I'll just do another one to get yourself familiar. Design a low-pass impedance matching network operating at 1 GHz for the source and load configuration shown in the figure below. Now you have, so you have to pretty much design a circuit here that is a low pass as well. So that means you need to allow DC to pass. That means you'll have one configuration. The inside will go as an inductor and a capacitor. So that inductor L and the capacitor C will form the low pass impedance matching circuit here. Now there are some design formulas, because if the source impedance RS here and the RL, if RS is smaller than RL, you can look at your design formula. So it's best if you guys keep them handy as well during your exam. Just take a printout or keep them with you. The design formula says that Q is given by RL over RS minus 1 square root, and then Q also gives you XL over RS and RL over XC. So these are the design formulas that you are normally given. Now it's if you need to find L, so we need to find Q anyway first. So RL is 1000 over 100 minus 1, so that's 9, and so Q is 3. Now if you want to find 3 equals XL is omega L divided by RS, so that also gives you 3 equals 2 pi F is 1 times 10 to the power 9 times L divided by RS of 100 ohms. So L can be found, and L will come to around 47.7 nanohenry. So same way you can find, so the Q is also given by RL over XC. In this case, RL, that's one answer before. XC is 1 over 2 pi FC. So that means if you rearrange them, C becomes Q over RL 2 pi F. From there you can get C to be 0.47 picofarad. So you got the two answers. Now what happens here is that you have an inductance of 47.7 nanohenry, and that is about 0.47 picofarad. Now when you do this L network matching, you assume the impedances are all real. But in this case, you have an inductor here and inductance here. So series and a parallel inductance. So this 47.79 Henry is what you need in the matching circuit to match the 100 ohm, a pure 100 ohm real impedance to a 1,000 ohm real impedance. So what you should do instead of, so the inductor here, the total inductance that should form should be 47.7. So this should be 44.7 nanohenry, because this and that added together forms a 47.7 nanohenry. And then you have a capacitor. You need a capacitance of 0.47 picofarad. But you don't need this 5 nanohenry. So this 5 nanohenry, you need to cancel this out. So I will just clear this out a little bit again. So what my point was here, what I add is not it's 44.7 nanohenry. And that came from 47.7 minus 3. Because that, so when you do the L network matching, you assume that's all pure real loads. Now this capacitor I have is 0.47 picofarad, and this inductance is there as part of the load. I just need to cancel this out. So if you want to cancel out an inductance, a parallel inductance, you can use a parallel capacitance. So this part, if I draw it again, I want some sort of capacitance to cancel out the inductance, which is 5 nanohenry. So that's L1, let's say, and this capacitance and this inductance should cancel out. That means this capacitance it's given by is total impedance of that 1 over j omega c should be j omega L. So you just don't need to so you have omega c, 1 over omega c equals 1 over omega L. That gives you omega squared equals 1 over LC. Now what you need to find is C, so you get 1 over omega squared L. That's frequency, it's 1 times 2 pi f squared times L. L is the inductance of 5 nanohenry, 10 to the power minus 9. And then once you solve that, you should get C1 here. So let's say C1 about 5 picofarad. So what it needs is another 5 picofarad, that to be 5 picofarad. So if I draw that, this should be 44.7 nanohenry, and it should have 0.47 picofarad and another 5 picofarad capacitance to cancel out this inductor. Now these two together will add in, because they are in parallel, the capacitors in parallel will add together. So this will two together will become 5.47 picofarad. So your final matching circuit will look like inductance of 44.7 nanohenry and a capacitor that's connected to the ground, which has a value of 5.47 picofarad. So that would be a final matching circuit. So that's how we work that out. So that's the only two questions I wanted to show, that because that involves a bit of workings, and you will get similar type questions that involve workings. And if you do workings, you need to upload that into the exam. So with that, I think that should be enough, and have a look through all the slides that I've given, notes, and prepare for the exam. All the very best, and thank you.